In this video, we will discuss about basic sequences or basic discrete time signals which we will be using throughout the course. The first one is unit sample or unit impulse sequence. This shows the picture of unit impulse sequence. So in x-axis, the values of n is written. So n stands for the number of samples. For example, n equal to 0 means 0 sample. N equal to 1, first sample. N equal to 2, second sample. N equal to 3, the third sample, and so on. So the unit impulse sequence is defined for different values of n, and the values are marked as shown in figure. You can see that the values are all 0 except for n equal to 0 where the value is 1. So we can define the impulse function as delta n. So please note down that delta n is the standard notation used for impulse. So during the entire course, when delta is mentioned, it always stands for impulse function. So delta n is defined as 0 for all values of n which are not 0. And the value of delta n is 1 when n equal to 0. So as you can see from the figure, n equal to 0 only you get the value is 1. So that is mentioned here. Now the second important sequence is unit step sequence. You can see the picture of unit step sequence. So as the name implies, it looks like step of a staircase. Only one step for a staircase here. So again, it is defined for different values of n equal to 0, n equal to 1, n equal to 2, n equal to 3, 4, 5, and so on. You can see that for n equal to 0, 1, 2, 3, 4, or n more than or equal to 0. That means this side of n values, the value of unit step sequence is 1. Whereas for all values of n less than 0, that is minus 1, minus 2, minus 3, minus 4, etc., the values are 0. So we can express it as an equation un. So again, u stands for unit step sequence, and this notation is followed throughout the course. So always u means unit step. So u of n is 0 for all values of n less than 0, that is for minus 1, minus 2, minus 3, etc. And u of n, the value is 1 for all values of n more than or equal to 0. That it refers to this side, n more than 0. Now there's another important sequence is exponential sequence. You can see that the value of the signal is exponentially changing. One example is x of n equal to k multiplied by a power n. So n values are defined here, n equal to say here minus 10, minus 9, minus 8, and so on. Now we will see in detail some exponential sequences. We assume k is 1. Okay, also can have any other values, no problem in that. So this picture shows for k equal to 1. In the first picture, the value of a is 0.5. So we start with n equal to 0. So we get k is 1. So 1 into 0.5 power 0. So anything to the power 0 is 1. So 1 into 1. So the amplitude is 1. Now n equal to 1 is a power 1. So a is 0.5, so we get 0.5. When n equal to 2, it is 0.5 square. N equal to 3, 0.5 cube, and so on. So we'll see the value is exponentially decreasing. Now we see the other case, when the value of a is more than 1. When a is 2, we'll see for first value, n equal to 0, the value is 1, n equal to 1, the value is 2, n equal to 2, the value is 4, and so on. So here it appeared like 0 because we marked the axis from 0 to 500, 1000, 1500. So this value, even though 2 and 4 and 8, 16, 32, 64, so they are all very close to 0 because of this higher scale. Same way, when a is minus 0.5, or a is between -1 and 0, you will see the values are alternately positive and negative as shown. When a is less than -1, the values go on increasing. Again, the values change from positive to negative for alternate values of n. Now we will see what is the shape for sinusoidal or cosinusoidal waveforms in discrete domain. So x of n is a discrete signal. It is defined as 10 cos 2 into pi by 8 into n. So pi is 3.414, as all of you know. The amplitude is 10 and frequency is 2 pi by 8 radians per sample for discrete signal. This shows the typical plot of this waveform in MATLAB. For n equal to 0, cos 0 is 1, so the amplitude is 10. For n equal to 1, the amplitude is 10 cos 2 pi by 8 into 1. So 10 cos 2 pi by 8 is the value. Then n equal to 2, the value becomes 0. Plus n equal to 2, this will become cos 2 pi by 8 into 2. So cos pi by 2, it is 0. We will see it follows a cosine wave. The envelope of this waveform is a cosine wave with the values sampled. We are taking only some values of cosine wave. Now we see how we will be able to represent discrete time signals, or they are also called as sequences. We can write discrete time signal in different format. So the first one is functional representation, where you can write x of n equal to 1 for n equal to 1 and 3. Again, x of n is 4 for n equal to 2, and x of n is 0 for all other values of n. Another representation is tabular representation. So we form a table with values of n along the first row and values of signal in the second row. So here x of n is 1 for n equal to 1 and 3. So I have written for n equal to 1 and 3, the values are 1. Okay. Now x of n is 4 for n equal to 2. Corresponding to n equal to 2, we write the value 4. Now the last one, x of n is 0 for all other values. So we populate all other values like n equal to 4, 5, 6, 7, 8, or n equal to 0, -1, -2, -3.